Hello. In this class, we'll discuss the equivalence of finite automata and the regular expressions or regular language. So, a regular language or a regular expression, suppose R is any regular expression and it is said to be equivalent to a finite automata, suppose A, if the language represented by, that is language represented by this regular expression R, is precisely accepted by the finite automata A. That is, we can say language generated by this regular expression R and language that is accepted by this automata A. And in order to establish this equivalence, we can do, suppose given a regular expression, and we can construct an equivalent finite automata. Now we have to prove that, suppose we are given a regular expression, and if we can construct an equivalent finite automata, or another way we can say that language that is generated by this regular expression which are basically accepted by this automaton A. And suppose to prove this, uh, given a regular expression, we can construct an equivalent finite automata. We need the following, uh, rather we can say we have to prove following three lemmas. There are three lemmas that we have to prove. Now to prove these three lemmas, first we'll assume that R1, suppose R1 and R2 are two regular expressions, are two regular expressions. And suppose there exists a finite automata A1 which is defined by, suppose Q1 sigma delta 1 Q1 and F1, and another automata, suppose A2, which is defined by Q2 sigma delta 2 Q2 and F2. Now this automaton A1 which accepts language generated by R1, and this automaton A2 accepts language generated by R2 regular expressions. Now we have to prove three lemmas. Number one, lemma 1. Lemma 1. What is this? Lemma 1, there exists a finite automata or automaton accepting language generated by R1 union R2. How we prove this? So we have to prove this lemma 1. That means, suppose we have two machines, automaton A1, A2, and we have already defined A1, what is A1 and what is A2. A1 accept language generated by R1 regular expression, and automaton A2 accepts language generated by the regular expression R2. Now there exists a finite automata which actually accepts language generated by both R1 union R2. Now uh, we draw a automaton. This is suppose this is automaton A1, which where the state is Q1 and final state is F1, F1, which basically accepts R1. And there exists another automaton, say A2, where accepting state is F2, right? And initial state is Q2. Okay. So now what actually we have to do, that if both language, that is R1 union R2, will be accepted by this automata. So now we suppose design the automata A. Let's see, this is our automata A which accept both, that is language generated by R1 union R2. So we make a new initial state Q naught and make a epsilon transitions to Q1 and another epsilon transitions to Q2, right? Now this automaton A will accept language generated by R1 union R2. So now to prove it, or suppose we are going to construct this automaton A which accepts both language generating by R1 union R2. Now say the automaton A, and we define Q, automaton A can be defined as A Q sigma del Q naught and F, where this Q, that means the new automaton A, what are the states of Q? The Q will be Q1 states union Q2 states along with the Q naught which is introduced in new initial states. Now what are the final states? That is F. It will be F1 union F2. And what will be the, and here Q naught is the initial state. Okay, this Q naught is the initial state. Now what will be the delta, or how we can define this delta in this new automaton A? It will be defined as Q cross sigma union epsilon to some subset. Say we define this as a suppose we define this suppose it is a subset, we denote it as it basically a subset of Q, subset of Q. So there is a mapping Q cross sigma union epsilon to subset of Q, and defined by this delta, these are basically defined as, or defined by, so del Q is any state and A is any symbol from sigma, that will be what, if you are, suppose if you are in state Q belongs to Q1 and A belongs to sigma union epsilon, means if you belongs to Q1, you belongs to a state, that means Q belongs to a state which are basically drawn from the automaton A1, and the input symbols, either it is A, where A is basically drawn from the alphabet sigma, and input symbol is epsilon. So what will be the transition here? Now the transition will be, in that scenario it will be delta 1, that means transition of the automaton A1. So delta Q comma A, where when if Q belongs to Q not Q1, that means state belongs to the automaton A1 and A belongs to this. Now what happen if Q, that means state belongs to Q2, that means automaton A2, and A belongs to sigma union epsilon? What happen in that scenario? It will be delta 2 Q and A. But what happen if your Q belongs to Q naught, means the initial state here? If Q belongs to Q naught, then what are the states after transition delta QA? So in that scenario, it will be, there will be a choice. It may be Q1 or Q2. And in that scenario, A should be equal to epsilon. Your input is epsilon, then you can go Q1 or Q2. So now we have defined this delta, right? And we have drawn the transition diagram. Transition diagram is basically this. Now, suppose uh, now x, now for x belongs to sigma star, we assume that any string x which is basically belongs to sigma star, new automaton A. So obviously x should be accepted by this, that means this string will be accepted by this automaton A. That means it belongs to the language which are accepted by this new automata A. So it basically implies that delta star starting from Q naught after processing X, and if we make an intersection of the final state, this should not be equal to empty. That means starting from Q naught after processing the string X, this X, and if we take the intersection with the final states of F is defined as F union F2, it should not be empty. So which again implies delta star, we can write Q naught epsilon X intersection F, which is also not equal to empty, which also implies that delta star and we can do this like it will be delta star Q naught epsilon comma X, then this X intersection F should not be equal to empty. Now what will be the value of this? If you are in Q naught after processing epsilon, what are the states that you can move? That means it will be delta star and the states will be Q1, Q2, and now X intersection of F should not be equal to null. And now again, so now delta star, so what will be happen here? Delta star Q1 X and or, it is or, so union delta star Q2 X. After processing this, so now if we make intersection with the final state, should not be empty. Again, so we can write this also, delta star Q1 after processing the string intersection F and union delta star q2x intersection of f should not equal to empty, which again implies, that means if sorry, it will be f1, right? No, f and f, and as it is delta q1, so it should be, so which we can again write in that way, delta star q1 x intersection f1 should not be null, or delta star q2 x intersection f2 should not equal to null. So what is the meaning of this? That means after processing x, starting from q1, after processing the state, if we make intersection with the final state of the automaton a1, these are basically with respect to automaton a1, and it basically is the automaton a2, and there is a or, right? So it basically implies that x belongs to the language accepted by the automaton a1, or x belongs to the language accepted by the automaton a2. So which implies that x belongs to language accepted by a1 union language accepted by a2. So in this way, that means language accepted by the final automaton A is basically equivalent to language accepted by the automaton A1 union language accepted by the automaton A2. Yeah. So in this way, we can prove that there exists a finite automata accepting this. Now, lemma 2. Lemma 2. There exists a finite automata or automaton accepting L1, L R1 R2. That is language generated by R1, concatenation language generated by R2. Clear? So now in this scenario, we can draw the diagram like that. Suppose this is our machine, that is A1, where it is Q1 state and it is F1. This is the final state. And another machine or automaton which is A2, it is F2 and it is Q2, and it is the initial state. And now there is that is A1 basically accepting the regular expression R1 and basically regular expression R2. Now we have to design a machine which accepts R1, R2. So in that scenario, we make that F1 should be non-final state, right? So we can draw in this way, it should be non-final state. And we have to draw a transition from here to here with epsilon moves, right? And the resulting machine, we can mean that it is a A. We can machine that it is a machine A which accepting a language generated by R1, R2. Now, again, we can define, that is the machine A. Suppose machine A which can be defined as we have defined previously. So Q sigma del Q1, and here it will be F2. because starting state will be Q1 and the final state or accepting state will be F2. Where what will be Q? Now here this Q will be the states of Q1 union the states of Q2. And here Q1 is the initial state and F2 is the final state. So now we define what is delta. So now delta can be defined as delta is defined as how? So we can write del, suppose any state A and A belong Q, any state Q and A belongs to any alphabet from this sigma. Now it will be, the situations are like if Q belongs to state Q1 and A belongs to sigma union epsilon. That means any state where this state Q belongs to Q1 and your input is A, where it belongs to the alphabet from alphabet sigma and epsilon. So in that scenario, this transition is basically equivalent to delta 1 Q comma A. Now if Q belongs to Q2 and A belongs to sigma union epsilon, then what happen? Obviously it will also the same. Q belongs to Q2 and A belongs to this, then in that scenario it will also be the delta 2 Q comma A. But what happen if Q belongs to F1? That means the state belongs to the final state of the machine A1, automaton A1, and your input is A is equal to epsilon. Then where you can go? It will be Q2 only. Because if you are in these states and your input is epsilon, you can move to Q2. Now we have defined the final automata this, right? Now what we claim here, what we basically claim. So our claim is that language accepted by this final automaton A is basically equivalent to language accepted by automaton A1, then language accepted by followed by language accepted by automaton A2. Now we assume that X is any string which is of the form A1, A2, AN, and it belongs to the language accepted by the automaton A, final automata A, or the resulting automata A. Now delta star Q1 X should not intersection of F2 should not be empty. That means starting from Q0, Q1, that means from Q1, after processing this string that we have assigned that X, and if we make the intersection with the F2, that is the final state of the final automaton A, where the final state is F2, so that it should not be empty. Now, from this automaton A, it is clear that to reach F2 from Q1, obviously we have to go through this state Q2. Again I repeat, starting from Q1, after processing this X, the string X, now to reach the final state F2, only way via the state Q2. Now, we have only epsilon transition that we have seen. We have this epsilon transition from the state F1 to Q2. That is epsilon transition from F1 to Q2 that we have seen. From F1, there is an epsilon transition to Q2, right? So thus, while we traversing through this x from q1 to some state, of f2. F2 is a accepting state. So to some state of f2, there exists state p which belongs to f1, and a number, that is k, should be less than or equal to n, such that p belongs to delta star starting from q1 after processing a1 a2 up to ak, and delta star from q2 then ak plus 1 ak plus 2 to an, and after doing the intersection with the f2, it should not be empty. What is the actual meaning of this? It means, that means while we traversing this x, that means from q1, and we have to reach some state, that is f2. So that means from q1 we have to reach to some state of f2. So there exists some state, that is some state q, which belongs to f1. That means from q1 we have to reach f1, and we assume that f1 is a set of final states. So there exists some state q which belongs to f1, and there is a number. That means while we processing the string, there is a number k which is less than or equal to our length of the string that we have assumed. So from q1 to up to that state, it will process the length having string k, and after reaching state q, then remaining string will be processed, that is a length k plus 1 to n, and it will reach to some states of f2, and if we make the intersection with the f2, it should not be empty. That is, the implication is that x1, which is considered as a1 a2 up to ak, that belongs to the language accepted by this automaton a1. That means we consider from a1 to ak, we consider that it is a x1. So the first automaton a1 will accept this x1, and x2 is basically equal to ak plus 1 ak plus 2 up to an, which belongs to language accepted by this automaton a2. That means it is basically x2. So we can say that x is equal to x1 and x2, which belongs to the language L. First string x1 accepted by L1, A1, and language accepted by A2. Yeah. So another way we can also, or alternatively, we can say, suppose x belongs to the language which is basically accepted by A1, A2. Then x is equal to, suppose, x1 x2 for some x1 which belongs to language accepted by A1, and x2 belongs to language accepted by A2 machine or A2 automaton. So that is, it means delta star processing from starting state q1 after processing x1, and if we make intersection with f1, it should not be null. And starting from Q2, after processing the string x2, if we make intersection with the final state of the automaton A2 should not be null. Right? So now del q comma x, q is any state and x is the string that we need to process. So which is basically we can write in that way. So it will be starting from q1 and the string is x1, x2. Here the starting state is q1. So after processing, after doing some steps, where we can reach? So we can reach a state q and we exhaust the state x1. That means remaining string is x2. What is this q? Q basically belongs to the state from f1. So for some q belongs to f1, right? So it basically equal to, so it is basically equal to uh, no, sorry, not, it should not be q, it would be p, some state p. It will be some, because there will be a confusion with the q. So now we assume that it is a p, right? Now after doing, so it will be p, we can write epsilon of x2, because there is a transition epsilon, we can write it because the string will remain same. Now what happened from this state, and p belongs to one of the state of f1. Now it basically equals to, because from state p, after the epsilon moves, go to the transition where we have defined, if q belongs to the state f1 and your input is epsilon, then you go to state q2. So that's why we can write it will be q2 state and x2, because del q and epsilon is equal to q2. Now this q is basically here, it is a p, because this, if q, this basically belongs to f1. Now after doing some steps, we'll reach to some state that is p dash, and the string is exhausted, that means epsilon. So for some p dash that belongs to the state f2, right? So hence we can say that delta star q comma x, sorry, q1x, delta star q1x intersection, oh sorry, it will be q1, I have mistaken here, because it is a q1, because always we have to process string from the state q1. So del q1 will be this. So delta star q1x intersection of f2 should not be equal to null, and hence we can say that x belongs to language accepted by this final automaton A. So that the x belongs to language accepted by the automaton A. Now third lemma, lemma 3. Lemma 3. There exists a finite automaton accepting language generated by R1, this star, or clean star, that is L, R1 star, that is R1 star, right? So now how we can prove this? L1 star means language generated by R1, that is language generated by R1 star which will be accepted by this finite automata. Right? So we can draw the uh, diagram like this. Suppose we have a automaton A1, because we need, that is A1. So starting from Q1 state, and we have to reach some final state, that is F. Okay, and this is a Q1 starting state. Now to accept Elon star language generated by this R1 star, not A1, R1 star. So there is basically a repetition traversing the path. Means after reaching from Q1 to F1, so to introduce this, we rather design the automata A accepting this language. We introduce a initial state Q naught, new initial state, and we have to make an epsilon transition from this initial state to Q1, and we introduce a state P, which is a accepting state. We assume that it is P, and it will no more final state, and it will be P, and there is a transition from this state, that is F1, with the epsilon moves to P. Right? And there is a repetition, that means from Q1, after processing this, you will go F1, then again go to the state Q1 through epsilon moves. And to accept epsilon, this there will be a transition from this initial state to the final state through an epsilon moves. Now this is basically the final diagram, which is basically the new automaton which accepting this R1 star. Now we define, so let's say the automaton A is basically Q sigma del Q naught and F, where this Q can be defined as Q1, the states of the automaton A1 union. We have introduced new initial state Q naught, so it will be Q naught, and we have introduced another final state, which is a P. Clear? So where this Q naught is the initial state, and there P is the basically the another state P, and P is basically considered as a final state. So F will be, that is P. Right? Final state will be P. Now how we define this delta? Now delta can be defined as so del from any state Q by taking a symbol A from alphabet, it will be, look, if this Q belongs to the state F1, that means you are here. This state Q is basically belongs to F1, that means one of the state of F1, that means here. And if your input A equal to epsilon and A equal to epsilon, then where you can go? So you can go from this state with epsilon moves to Q1. So one of the state will be Q1, and with epsilon moves or with epsilon moves we can go to state P, so it will be P, and it is a if. Right? Now what happen if Q belongs to Q1 state and A belongs to any symbol from alphabet sigma and union epsilon? In that scenario, It will be equivalent to the transition of delta 1 q comma a, right? So now we have defined this delta function by this way. Now our claim is, what we are going to claim, and we have to prove that language accepted by this final automaton A, which is language accepted by this basically A1 star. Now for x is any string that is basically belongs to this sigma star. So x should belongs to language accepted by this automata A, implies that delta star starting from q naught after processing x, it will be in the final or accepting state P. Now in this scenario, this x may be epsilon or it may be a string. So either, so which also implies that either x is equal to epsilon, or what happened, or delta star q naught x, an intersection of f1 should not be null. F1 is accepting state of the automaton A1. So in this scenario, either x should be equal to epsilon, or delta star q naught x, that means from initial state q naught after processing x, and what are the state that you obtain if we make an intersection with the final state of f1, that is automaton a1, that should not be empty. Now if in this scenario, if x is equal to epsilon, that means x belongs to language accepted by A1 star. Clear? Otherwise, because if excellent, that means it will be accepted by this automaton A1. Otherwise, there exist some states like suppose P1, P2, some states Pk, which are basically belongs to the accepting state of F1, and x1, x2, xk is the string, such that P1 belongs to delta star from state q1 x1, P2 belongs to delta star q2 x2. In this way, pk belongs to delta star q1, sorry, no, yeah, it will start from q1, no, it will be 1 q1, it will be q1 and xk, meaning because there is some states p1, p2 or pk which belongs to the final state of f1, that means automaton a1, and some string is suppose you can say x1, x2 and xk. So now p1 would be the state belongs to the, after processing the string x1 starting from q1, so the state p1 belongs to this. P2, it will process the string x2 starting from q1, and pk will be the state which belongs to after processing the string xk starting from q. That means with x is equal to x1, x2, xk for all 1 less than equal to I less than equal to k, xi belongs to the language accepted by A1. Because suppose our diagram is this. So now string, so F1 is basically the accepting state for the automaton A1. Now x1, so from q1, after processing x1, you may go to some state that we assume that is a p1, which is basically belongs to one of the state of f1. After processing x1, you'll go to this state and it retraverse here. Then after processing the state x2 and so on, in that way it will be process x1, x2 and so on. And when there is an epsilon, so from q naught, after processing epsilon, it goes to the state p, which is accepting state. So thus xi belongs to the language that is basically accepted by the automaton A1, and we can conclude that x belongs to the language that is which is accepted by A1 star. So this is basically the proof of the lemma 2, or another alternative way we can also prove. So alternatively or conversely, suppose x belongs to the language accepted by A1 star, we assume it, then x, we assume that it is a x1 x2 dot 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 xl of length l, with x of I basically belongs to language accepted by the automaton A1. For all I and for some L which is greater than or equal to 0. Now if L equal to 0, that means the x which is equal to epsilon string of length 0, that means epsilon x is equal to epsilon. So clearly x belongs to language accepted by this automata A. Otherwise there should be a path, that is delta star, starting from q1 after processing each string xi, and if we make intersection with the state f1 should not be empty. For 1 less than equal to I less than or equal to L. So we have to process each xi, and the result that will be returned by this, if we make intersection of f1, that is final acceptation, should not be empty. It gives some state which is basically the accepting state. Then we can say that the each x of I will basically accepted by the language accepted by A1, automaton A1. Now we consider the following computation of A, that is automaton A, on the string x. So now we have to process the string x for the automaton A. That means now the starting state will be q naught. So we can write uh, del we can write q naught, that means starting from q naught after processing x. What we can write from q naught, we can just write that there is an epsilon x. So now if your input is epsilon from q naught, if your input is epsilon, you go to state q1. So now we can write the move uh, it will be this. Now the move will be, it is a q1 and x. So which is basically, we can write you are in q1 and the string is basically x1, x2 and it will be xl. Now after doing some steps, more moves, that is star, you are reaching some state p dash, that is p1 dash, some state, and you have processed the x1. So now remaining string is x2, xl. Here what is p1 dash? P1 dash is basically belongs to some state of f1. Now what happened after doing this from p1 state, and again that means you are now in this state p1 dash, right? And p1 dash belongs to f1, one of the state of f1. So if you are reaching this, after epsilon moves you go to q1 state, right? So we can write, it will be p1 dash, we just add epsilon, then x2, that xl, to meaning to clearly that there is an epsilon moves. So now after this moves, it will go to some state q1 and remaining state is x2, x3 and so on, it will be xl, right? Where q1, what is q1? Q1 belongs to delta star from q0, sorry, p1 dash from delta star and from p1 dash comma epsilon. It is basically q1. It returns q1. Now in this way, after processing some steps, so it will be look like that. It will reach the state. Suppose it is a pl dash, and the string is basically xl, that is exhausted. So you can write this epsilon, right? Now once you are again pl dash is also belongs to this f, on of the accepting state of f1. Now if it happens, that means you are again here. Now you have epsilon moves, so you can move here or you can go to final state, but now we have to move final state. So now we can write after these steps, it will be p, it will be, the state name is p, so it will be now p, it will be p and the epsilon, since what is p? P basically belongs to delta star pl dash comma epsilon, and string is exhausted, or we can write the state is p only. So what we conclude from this, that means starting from q naught, after processing the string, if we make intersection, it is basically not empty, and hence x belongs to L of A, language accepted by A. This is basically the alternative way to prove this lemma, and we have shown here the computation on the automaton A, that is final automata, automata A with a string that is basically x, and this string x is basically considered x1 x2 up to length L, where this length L is basically 1 to for any I. So basically meaning is from q1, after taking x1, we go to some state which basically belongs to the final state of f1. Any state belongs to f1, and from here through epsilon moves we go to here. So again and again we repeat this path to process the entire string, and after that, when the string is exhausted and you are reaching one of the final state of f1, through epsilon moves you go to final state, accepting state p, and the string is accepted. And if the string is epsilon, that means string of length 0 that is accepted. At that time there is a from q naught through epsilon move, so you go to state p. Obviously at that time epsilon will be accepted by this automaton. So finally we conclude that the that uh, L language accepted by this automaton A is basically language accepted by the automaton A1 star. Thank you.